Hey there! In this video, we're going to continue our study of mathematical induction. If you haven't watched the comfort Zoom or the previous video, then that's okay. I'll recap a little bit in here and then we'll move on to the next example. But the principle of mathematical induction is essentially if you have a statement about n, and if the following two conditions are satisfied, then we can say that that statement about n is true for all n, all the way from 1 to infinity. So the conditions to satisfy the principle of mathematical induction are that the statement about n has to be true for n equals 1. So that's what P of 1 is, right? If P of n is a statement about n. And the second statement is that for every natural number, or the second condition, sorry, for every natural number k, if P of k is true, then P of k plus 1 is true. Meaning if the statement about n is true for n equals k, then that same statement is true about n for n equals k plus 1. So in class I talked about the dominoes falling, and there are other different things. I also shared this little graphics. Let me see if I can reshare it here. This little comic that is in the textbook. And so what this says, let's see if we can make it even bigger. So there are these people that are looking at this ladder. Notice, trying to make it bigger here. Notice that the ladder starts in the middle of the wall and then it goes up. And so this one person on the left here says, if I were on rung number k, then it will be easy to get to the next rung. And then you can climb the whole ladder. The other person says, sure, and then you could climb the whole ladder. And then this person on the right says, but one has to manage to reach the first rung first, right? To begin with, you have to get to the first one. Once you get to rung number 1, then you can, if you get to the kth one, sure, you can climb the whole ladder. So that's the idea of the principle of mathematical induction. And if you think about stacking dominoes and see if you can make them all fall, right? If the first domino doesn't knock over the second one, the rest are not going to fall. And so we can kind of go with that idea. There's also a joke. Let me see if I can remember it, but it's about mathematicians and physicists. It's how many physicists does it take to change a light bulb? And the answer is 3. 1 to hold the light bulb in place, and the other 2 to rotate the universe around. So if you've taken physics, or it's funny. Even if you haven't taken physics, essentially the two physicists are rotating the world around to screw in the light bulb. So, but then the mathematical induction part comes in, is in the second part of the joke. How many mathematicians does it take to do the same job, to screw in a light bulb? And the answer is 1, because the mathematician will hire the 3 physicists to do the job. And so essentially 1 can do it, and then you can go on that way. How many, if 1 can do it, right, then if it's true for 1, then you can just kind of assume that same principle all the way around. So then this is the principle of mathematical induction. So show that it's true for n equals 1, assume it's true for n equals k, and then show it's true for k plus 1. Once those essentially kind of like 3 conditions are met, then we can say the statement is true for all n. So let's prove this. So the sum of all the squares is equal to this formula, n times n plus 1 times 2n plus 1 over 6. And this one, for those of you going on to taking calculus 2, you'll see this formula in calculus 1 actually first, and then you'll see it again in calc 2. Okay. So how do we prove that? It says, our mathematical induction, show true for n equals 1. So we're going to go with that part. 1. We want to show true for n equals 1. So that means that we want to say 1 square, right, first term here, 1 square is equal to 1, plug in the 1 into all the n's in here. 1 times 1 plus 1 times 2 times 1 plus 1 over 6. Now notice that this gives you 1 times 2 times 3 over 6, which is really 6 over 6, which is 1. So it is true for 1. So the second principle of mathematical induction is an if-then statement. Okay, so if P of k is true, then P of k plus 1 is true. So with an if-then statement, that means you get to assume the P of K. So let me write the assumption. So the if statement, that means we assume the statement is true for n equals k. So that means that 1 squared plus 2 squared plus 3 squared plus 4 squared and so on plus k squared is equal to k times k plus 1 times 2k plus 1 over 6, right? This is our end statement. So we're saying it's true for n equals k. So everywhere you see an n, plug in the k. So we are assuming that that is true. Then p of k plus 1 is true. So that means we want to show that is what an if-then statement is. If this is true, we need to show that the then part is true. So we want to show that 1 squared plus 2 squared plus 3 squared plus dot dot dot. I always write the k term and then, so this is, we want to show that this is equal to, now we're replacing every n with k plus 1, right? So that's where I'm going over here. This is the statement about n. So replace the n with k plus 1. So this is going to be k plus 1, k plus 1 plus 1, 2 times k plus 1 plus 1. So let's make sure we can see it. So I'm going to have k plus 1, right? Replacing the n with k plus 1. K plus 1 plus 1 will give me k plus 2. And then 2k plus 1 and then plus 1. The whole thing over 6. Let's simplify this so that it looks better. So I have k plus 1 times k plus 2. What is this? 2k plus 2 plus 1. So 2k plus 3 all over 6. Okay, so this is what we want to show. So right now I'm going to put question marks. And remember, with the proof, work on one side and get to the other. You can work on, like in terms of simplifying sides, but what I mean about work on one side is this is not an equation, so don't be moving terms from one side to the other. You're supposed to stay strictly on one side, simplifying it. In this case, I am simplifying this side, but notice I'm not moving things from one side to another. Okay, so this is what we want to show. But from our assumption, our principle of mathematical induction, our assumption tells us that this is true. So then I know that this part equals that formula. So 1 plus 2 squared plus 3 squared plus k squared. So stopping there, I know I can replace this whole thing with what it equals because we're assuming that that statement is true. So I can replace this with the formula. So this is equal to k times k plus 1 times 2k plus 1 over 6. And then I have plus my k plus 1 squared. So I'm going to continue just working on the left side. And here I want to simplify it. Okay, so don't multiply it all out. That's going to get messy. Notice that I have a k plus 1 and a k plus 1 square. So I'm going to think about factoring. So factor out the k plus 1. So when I factor out a k plus 1, I'm left with k times 2k plus 1 over 6. Over here, right, we take the k plus 1 out. Plus, I'm taking one of these out, but I'm still left with 1k plus 1. So does that equal that side? Let me rewrite it so that we don't lose it as I keep scrolling to the top. So that's what we want to see. Okay, so now here I do want to multiply stuff out and simplify. So I have k plus 1 that I factored out, and let's work on the inside here. So distribute this k. So I have 2k squared plus k over 6 plus k plus 1. Let's get a common denominator here. Right, I'm gonna want to add these. So let's multiply both sides, or top and bottom, by 6. So once I do that, distribute the 6. So I'm going to have 6k plus 6 over 6 because I want the same denominator. So I'm going to have my k plus 1, the one that we factored earlier, and now everything is over 6. So let's combine like terms. So I have 2k squared plus 7k plus 6. And so does that equal what I have on the right. Well, we have the k plus 1, so that's a good sign. Notice that we do have our k plus 1 at least there, so now we need to figure out what about the inside. So looks like we can factor the inside. So what are two numbers that multiply to 6 and add up to 7? And, oh wait, two numbers that multiply to 12 and add up to 7. So 4 and 3. And you can do however you want to factor that, the box method, and reduce it, but we do end up getting k plus 2 times 2k plus 3 over 6. And just double check me here. Notice that I get a 2k squared, 3k plus 4k is 7k, and then 6. So that gives us that, and this is in fact equal to this, right? Notice that once I put everything over 6, because this is just multiplication, so numerator times numerator, denominator times denominator, so yeah, I'm going to have k plus 1 times k plus 2 times 2k plus 3 over 6, which is what we have on that side. So we did it. So what did we show? Let's go through. We showed that it's true for n equals 1. We need to show this if-then statement, so we assume it's true for n equals k. And then we show that it's true for n equals k plus 1, which is what we did here. So the two statements, the two conditions are satisfied. So in our principle of mathematical induction, 1 and 2 are satisfied, which means the statement is true for all n. For all n. So that means that 1 squared plus 2 squared plus 3 squared, right, this was our statement, plus n squared is equal to n times n plus 1 times 2n plus 1 over 6 for all natural numbers n. All right, so that is another example of mathematical induction. I encourage you to watch the comfort Zoom or the previous video as well. And email me if you have any questions.